Hi, good evening. So today we're going to solve some examples on shear force and bending moment diagram. We're going to cover everything from cantilever beam, simply supported beam, overhanging beam, subjected to different load cases like uniformly distributed load, a point load, or a uniformly varying load, etc. So let's start off with a very simple example. This is about a cantilever beam with the below specifications. This is the fixed support, this is your beam. We have a 300 newtons of point load at one point, 500 newtons of point load of one point, and 800 newtons of point load at the end. Now the spacing between these point loads is 0.5 meter, 0.7 meter and 0.8 meter. Let's call this A, B, C and D. Now in order to start off with the drawing of shear force and bending moment diagram, we have to first calculate the shear forces and bending moments individually. So let's calculate the shear forces. Let's start with shear force at D, that is this point. We have 800 newtons acting downwards. Since it's a point load, it is a constant, it's constant throughout the entire beam. So shear force at point B should be 800 newtons. Since the right hand side of the section is downwards and the left hand side section being upward is represented as positive shear force, this would be plus 800. I can just give a small, if this is a section, let's just say xx. If the right hand side force is downwards and the left hand side force is upwards, this can be considered as positive shear force. Next, moving on, shear force at C, right, towards the right of the C. So we are going to consider the shear force just to the right of C. We are not going to include C here because we want to see the exact amount of force that has been reflected just before the incidence of another 500 newtons of force. So just towards the right of the C, we have a shear force of 800 newtons, which is going all the way across. Since it's a constant thing, it would be plus 800 newtons. Moving on, shear force at the rate left of C. So just to the left of the C, we have another 500 newtons that is added. We have included the C point, so we have 500 plus 800, that would be 1300. So I'll just put 500 plus 800, 1300 newtons. Everything is positive. Moving on, shear force at right of B, B right. So up to B, without including the force at B, we have a force of 800 and 500 combined together acting just before the point B, that is where the 300 newtons is acting upon. So that would be 500 plus 800, that is another 1300 newtons again. Shear force at left of B. So just towards the left of the B, we have the 300 included, so that would be 1300 plus 300, that is 1600 newtons of shear force, positive. Since everything towards the right acting downward is considered positive, we have 1600 as a positive shear force. Moving on, shear force at A. Shear force at A, which is the final point where all the shear forces, all the forces acting downwards are reflected towards the end point. So it is 1600, which is 800 plus 500 plus 300 all together combined, that is 1600 newtons, and it is positive since just towards the right everything is acting downward, so it is positive. So these are the shear force values. We have 800, 800, 13, 13, 1600 and 1600 newtons at different points of the cantilever beam. Now let's check the bending moment values. bending moment at D. Bending moment at D. So when the moment is acting, there is usually moment is defined as load times the lever arm. Whatever load is applying, it has to be multiplied to the lever arm. So the load of 800 newtons is acting at a point which has no dimension to itself. So load into the lever arm length is 0. So 800 times 0, that would be 0. 0 Newton meter. The unit of bending moment is Newton meter. So bending moment at D is 0 Newton meter. Bending moment at C. Now at point C, we have 800 Newton acting at one end along with the lever arm. Now we have a dimension for that particular lever arm, that is 0.8 meter. So it is 800 times 0.8, that would be 800 into 0.8, that should give you 640 Newton meter. Now if you recognize, I have represented this with a minus sign because when it comes to bending moment, if there is we can represent the sign notation in two forms. The first form is hogging and sagging action. The second form is the movement in terms of clockwise and anti-clockwise directions. For instance, let us just consider a fixed support with a cantilever beam. Now I'm just considering this eraser as a beam section over here. So if I ought to apply a load, if this is the fixed section and this is the free end, if I am applying a load, if there is a hogging action in the cantilever beam, that is the beam is hogging, this is called hogging, the beam is hogging, we consider the moment to be negative. For instance, if we consider the same case where if this is a simply supported beam where this is supported on my this is supported with my two fingers, and there is a load applying at the center and the beam is sagging. This curvature which is representing on the top part is creating a sagging moment. So in case of sagging, we consider this as a positive bending moment. Similarly, in a cantilever beam, if the load is being acting from the bottom direction towards the top, it creates a sagging action. So that comes as a positive moment. And while we are at it, let's talk about the second way of looking about the sign conventions in with regard to the moments. For instance, there are many nomenclatures where anti-clockwise and clockwise are considered to be positive or negative, the other way around. Whichever it is ideal to consider one standard one throughout your entire process or procedure of solving the problem. So for instance, if the beam is creating a clockwise moment, if it is moving in a clockwise direction, we consider it to be a positive bending moment. If the beam is creating an anti-clockwise moment, we consider it to be a negative bending moment. It can vary, you can either consider the other way around, but the main idea is to make sure that you follow it throughout the same aspect. For instance, if in this particular case, when the load is acting over here, it is turning the beam in an anti-clockwise, it is turning the beam in a clockwise fashion. And if you think the load is being applied over here with the fixed support on the right hand side, it is turning the beam in an anti-clockwise direction. If this is the case where towards the left hand of the section is anti-clockwise and towards the right hand of the section is clockwise, we can consider that as a negative bending moment. Similarly, just like how the hogging is happening over here, clockwise movement, hogging action, we consider it negative. Anti-clockwise movement, though it is a hogging action, we consider it negative. While we are at it, let us also discuss the another kind of sign convention with regard to the bending moment. For instance, if the moment is creating a clockwise movement, if the load is creating a clockwise movement towards the right hand side, it is considered as a negative bending moment. If the load is creating an anti-clockwise movement towards the left hand side, it is considered as a negative bending moment. Similarly, for positive case, if the load is creating an anti-clockwise movement on the right hand side, or if it is creating a clockwise movement on the left hand side, it is considered as a positive bending moment. Let's just solve the problem so that it will be much more easier to comprehend while we are doing so. So over here, let's just take the hogging and sagging style of sign convention over here. It is much more easy and visually more comprehensible. So if this is a fixed support, the load of 800 newtons is acting at the end, it is creating a hogging action. So hogging action is negative moment. So minus 800 times 0.8, that is 640 Newton meter. Now, now moving on, let us calculate the bending moment at B. Bending moment at B is, it is basically the algebraic sum of all the moments happening from one direction to another direction. So it is 800 times the total lever arm length, 500 times the remaining lever arm length. So minus 800, since it's hogging anyway, times 0.8 plus 0.7 plus minus 500 into 0.7. So this should give us 0.7 plus 0.8, that is 1.5, 1.5 and 500 times 0.7, that is it is summing up to a total of 15 Newton meter. And since plus into minus is minus, everything should be in minus, so it is a negative bending moment. Or you can just identify it as all the moments are acting which are causing a hogging action, so the moment would be negative anyway. Moving on, lastly, bending moment at point A. Bending moment at point A, I'll just directly try to put the values here. 800 times total lever arm length, so minus 800 into 0.8 plus 0.7 plus 0.5, I think that totals to 2, plus into minus 500 times 0.7 plus 0.5 plus minus 300 into 0.5. Plus and minus minus, so all this would sum up to minus 800 times 2 plus and a minus, so that's minus 500 times 1.2 minus 300 times 0.5. So this is 150, this should be 1600, this sums up to minus 2350 Newton meter. So we have all the bending moments at different points, bending moment at A, bending moment at B, bending moment at C and D as well. So let's get on to drawing the bending moment diagram for this particular beam section, cantilevered beam. So I'm just going to put the same diagram, just slightly bigger. I have 800 newtons here, 500 here, 300 here, at 0.5, 0.7 and 0.8 meter length. I'll just represent the points again. This is point A, this is point B, point C and point D. So I'm just going to extend the lines a bit so that it will be easier for drawing the bending moment diagram. So first I'm going to draw the origin, the x-axis for shear force and bending moment diagram. So let's consider this as the x-axis for shear force and this as the x-axis for bending moment diagram. Let's start with the shear force diagram. So shear force at point D, it will be more convenient if you can extend the lines where the loads are interjecting, because it would be easy to mark. Right. So shear force diagram, shear force at point D, we have 800 newtons acting positive. So this is the x-axis. Anything below x-axis is negative, above x-axis is positive. So we have 800 newtons. Let's just think 800 newtons is over here on point D. Next, shear force to the right of C, just towards the right of C, we have again 800 newtons. Now shear force to the left of C, we have 1300 newtons, that is including C, we have 1300 newtons. Next, shear force to the right of B, this point, we have another 1300 newtons. Shear force to the left of B, we have 1600 newtons here. And lastly, shear force at point A, we have 1600 newtons. So now that we have marked all the shear force points at different with respect to the data which we have, let us just join all the points. Since point loads on cantilever beam will give you a constant representation on the graphical part. Point load, the shear force for a point load will be constant, so there will be no inclination of lines or any of such. It's all straight lines. So you just hatch that. So this is your shear force diagram. It is positive. Next, coming to bending moment diagram, let us see bending moment at point D, it is at 0. So this is the x-axis, which is the 0 axis. So the bending moment at point D is 0. So we don't have anything that is changing. Next, bending moment at C, it is minus 640. So anything below the x-axis is negative. So let's consider bending moment at C 640, somewhere over here randomly, 640 Newton meter. And next, bending moment at B, it is 1550. It's nearly a double. So let's just go to this point, minus 1550, that is by negative. So minus 1550 Newton meter. And bending moment at A is 2350. I'll just extend a bit. I'll just consider this as 2350 Newton meter. So I'll be joining these lines. And let me just hatch this. So this is the bending moment diagram and this is the shear force diagram. Since everything is happening below the x-axis for the bending moment, this is negative. This is how you draw the shear force and bending moment diagram for a cantilever beam with 3 point loads distributed with different spacing. Welcome back. Let's just let's just solve another example with regard. Welcome back. Let's just solve another example with regard to the representation of shear force and bending moment diagrams for a cantilever beam. This time we'll just try to complicate the problem a bit by incorporating a UDL along with point load together. So here's the problem. We have a shear force, we have a fixed support with a cantilever beam. Let's just say it has 3 kilonewtons of load. So So let's solve another example with respect to the shear force and bending moment diagrams. This time we'll complicate the problem by incorporating two different types of load. We'll have a point load, we'll have 2 point loads and a UDL somewhere in between here. So this is a fixed support. Let's just name our points. This is A, this is B, this can be E, sorry, A, B, C, D and E, either way, whichever works. The nomenclature is not important. This is a UDL with 1 kilonewton per meter. So let's calculate the shear forces first. Shear forces. Shear force at point B, that is this point, this should be equal to, since it's a point load, it's 2.5 kilonewtons acting downward, right hand side of the section, so it's a positive shear force, so that will be 2.5 kilonewtons itself. Shear force at C, to its right of C. So since until point C it's just 2.5 kilonewtons, we didn't have anything included at point C, there is no point load as well, so it is 2.5 kilonewtons. That would give us the same value, 2.5 kilonewtons. Next, moving on, shear force to the left of C. Here we have a 2.5 kilonewton acting downwards and positive. Also towards the left of C we have a 1 kilonewton per meter UDL run that is acting towards the left of C all the way up to D. So we have to consider this load as well. So in order to include that, let's just put 2.5 kilonewtons first, which is acting downwards, plus the 1 kilonewton per meter UDL, and this is spanning across this particular dimension from D to C. I'm sorry I didn't write any dimensions here. Let's just put some dimensions. Let's call this 1 meter. This can be 1.5 meter. This can be 2 meters. And this can be left with 0.5 meters. So let's calculate the shear force towards the left of C, that is 2.5 kilonewtons acting downwards plus 1 into 2 meter run, so that is 2 by itself. So this would sum up to 2.5 plus 2, that is 4.5 kilonewtons. So we just multiplied the total UDL that is happening per meter into its total length of run. So that is 2 meter of span, which is the UDL on which the UDL is acting, which is why we have multiplied that in order to get the shear force at point towards the left of C. Next, shear force at point D. Here we need not consider left or right of the point because it really doesn't make a difference, since this is not a very deciding point on a cantilever beam, a determining point on a cantilever beam of how the load might be varying. So we can just do the same thing. There is a 2.5 kilonewton acting downward, there is a 1 kilonewton per meter UDL acting downward. So even at point D, left of C or point D, it is pretty much the same amount of shear force that is acting. So 1 into 2, that is 2, 2.5 which is acting downward, plus 1 into 2, that is 4.5 kilonewton. Shear force at E, right. Now why I have considered towards the right of E is because at point E we have a determining factor of an extra load, that is 3 kilonewtons. So we do want to calculate the difference or the change of loading that is happening from this point. That is the reason why we are calculating one towards the right and one towards the left. So towards the right of E, we can, towards the right of E, yes, we have only 2 loads that are happening towards the right of the right of E, that is 1 into 2, that is the UDL for shear force with respect to the uniformly distributed load, and shear force with respect to the point load. So that's pretty much the same value which we get from the above. It is 2.5, the point load acting downwards, and the UDL 1 into 2, that is 4.5 kilonewtons. Shear force at left of E. Now towards the left of E, we are having this factor, we are having 3 kilonewton point load acting downward, which this is included in the entire shear force that is happening towards the left of E. Now it is 4.5 kilonewtons that is happening up to up to E, and a 3 included, that is 3 kilonewtons. That would be 7.5 kilonewtons of force acting towards the left of E. Finally, shear force at point A. Shear force at point A, there is nothing special that is happening in between these two spans. Whatever that is happening till this point is reflected all the way till the fixed support. So it would be 7.5 kilonewtons. Now that we got our shear forces, let us calculate the bending moments. Bending moment at point B. Since we're starting here, bending moment at point B, load times lever arm is 0 length over here, so 2.5 into 0, that is 0 kilonewton meter. Bending moment at point C, load times lever arm at point C, we have 0.5 length, the length of the lever arm is 0.5, so 2.5 times 0.5. Since this is creating a hogging action, again it is negative, so minus 2.5. This will give us 2.5 times 0.5, that would be 1.25 kilonewton meter. Bending moment at point D. Bending moment at point D, we have 2.5 acting with the entire lever arm. So 2.5 into 2 plus 0.5 minus 2.5 into 2 plus 0.5, that is 2.5, plus we have a UDL, again be negative since it's acting downward, it is causing a hogging action. So that is 1 into the length 2 meter into half of 2 is exactly 1 meter, so this would be 2 by 2. Now you might be wondering why we did 2 by 2 over here. If you can recall, or if you can just revise through your books, we know that the bending moment for a uniformly distributed load is WL square by 2. So we have W, that is 1 kilonewton, this is 1, L, that is 2, L square, so 2 square, that is 2 into 2, divided by 2, so divided by 2. On the whole, we get the total value as 2.5 times 2.5, that can be, and we can just put this. So this is summing up to 0.825 kilonewton meter. This is the bending moment at point D. Moving on, bending moment at point E. So at point E, we have all the same things acting downward, but there is a change in the lever arm. So it is 2.5 times the total lever arm length over here, that is 1.5 plus 2 plus 0.5, that can be minus 2.5 into 0.5 plus 1.5, that is 2, 2 plus 2, that is 4. So that is the total lever arm length plus 2 minus of 1, that is UDL, into into 2, that is the span on which the UDL is acting, into again 2 by 2, that is the L square, plus 1.5, and this is half, this is 1, so this point is 1. So 1.5 plus 1, that is 2.5 meter. So that is the total amount of UDL acting at point E. Now, if you might be wondering why this 2.5 has occurred is the possible question. So let's just look this in terms of lever arm. For a point load, we are multiplying the lever arm up to the point where we want to calculate the moment. So it is the load, that is 2.5 kilonewtons, into the entire lever arm length, 0.5, 2 and 1.5 altogether. Similarly for UDL, it is the load UDL 1 kilonewton per meter, which is acting on a span of 2 meters, that is 1 into 2 times the entire length at which we want the bending moment from the midpoint of the UDL, because we know when the UDL is converted into a point load, the point load acts exactly at the center. Now when it acts exactly at the center, it is going to split the span equally into two halves. This is, in this case, it is 1 meter and 1 meter. So if this is 1 meter and 1 meter, if the point load of 1 kilonewton is acting exactly at the center of this particular span, 2 meters, 1 into 1 plus 1.5. So that is how we got the 2.5 value, or that is how we usually calculate the point load bending moment over here. So this will give us minus 15 kilonewton meter. And lastly, let us just calculate the bending moment at point A. So again, we have another increment of 1 meter in its lever arm length. So 2.5 times the total length, 1 kilonewton per meter, times the total length up to point A, 3 into the remaining length of 1 meter. So that's 2.5, again minus, into the total length, 1 plus 1.5, 2.5 plus 0.5, that is 3, 3 plus 2, 5. Plus and minus 1 kilonewton times WL square by 2, that is 2 into 2 by 2, plus we have the length 1 plus 1.5 plus another 1 over here. So that would give us 2.5. So 1 into 2 into 2 by 2 plus 2.5 would be the moment that is caused with the UDL happening over here. So this would give us, we have another load that is minus 3 kilonewtons acting the lever arm of 1. So on the whole, we have 2.5 times 5, this would be minus 1.25 minus just minus 2 minus 0.5. On the whole, the total value, I will be getting it as 22.5 kilonewton meter negative. So this is the bending moment at point A, that is 22.5 kilonewton meter. Now let's just represent all this data in terms of a bending moment diagram. So I'm going to just draw the same beam. It is advised to draw these lines because it will be much more convenient and less confusing when you're drawing the shear force and bending moment diagrams. So I have my two x-axis for shear force and bending moment. This is the x-axis for shear force and the bending moment, x-axis for the bending moment. Let's start with the values which we have over here. Shear force at point B, it is 2.5. I'm just going to mark it over here, 2.5. Shear force at point C towards the right of the C, that is 2.5. Just mark 2.5 here. Shear force to the left of C, it is 4.5. Left of C, I'll just put 4.5 over here. Again, shear force at D, 4.5. Next, moving on, shear force at right of E, just right of E, it's again 4.5. Left of E, there's an increment, let's put 7.5, and shear force at A is 7.5. Everything will be in kilonewtons, so make sure you put that. So for the point load which is acting at point B, 2.5 kilonewtons, we're going to have a shear force that will be linear, but between D and C we have a uniformly distributed load where the shear force will not be linear. We cannot join linear lines, constant lines. For a point load, the line should be constant, but for a UDL, it cannot be constant. For a uniformly distributed load, the shear force will always be linear. So you cannot join these 2 points, 4.5 kilonewtons together, because it is not the right practice. It's not the right way of doing representing a shear force diagram for a UDL. So we connect it linearly between the lowest and the highest point of the shear force. Again, we have a point load between these two, so again we don't have anything to do with the linear force, it will be constant. And lastly, we have point load over here, so it will be constant. So except for the place where the UDL is distributed, we have a linear diagram. Since all of our shear forces are on the positive note, everything will be above the x-axis. That is the reason why we got the graph towards topward. So everything is positive. Now let's come back to the bending moment. Let's go, start the bending moment diagram here. The bending moment at B, it's 0, so there's no change over here. Bending moment at C, we have 1.25. I think this should be minus 1.25 because it is negative 1.25. So I'll just put that BM at C somewhere over here, minus 1.25. Then bending moment at D, minus 8.25, bending moment at E, minus 15. This is increasing a lot, minus 15. And bending moment at A is minus 22. We'll just put it over here, 22.5. Let me just extend this to these points. So for a point load, when you're drawing the bending moment, it's linear over here. But for a UDL, the bending moment cannot be linear, it will be parabolic. So we cannot go with a linear graph over here or a linear line over here. The graph or the line should be parabolic. So that's the parabolic part over here. Again, it's point load over here, so it will be linear again. Again, it's point load over here, and lastly it will be linear again. So everything is happening on the negative side, that is below the x-axis. So the bending moment will be negative. This is how you calculate the bending moment and shear force and represent that in diagrammatic representation for this particular problem. The key takeaways for this problem is, for a uniformly distributed load, the bending moment, bending moment diagram would be parabolic, and for a uniformly distributed load, the shear force diagram will be linear. For a point load, the shear force diagram will be constant. For a bending moment, for a point load, the bending moment diagram would be linear. So these are the two key takeaways from this particular point. Also, it is noteworthy to mention that the way we calculate the uniformly distributed load at this particular point with respect to the bending moments at different points. For instance, if you want to calculate the bending moment with respect to D, with respect to the UDL, we can apply the formula WL square by 2. This will give us the bending moment at point D. But if you want to calculate the bending moment at point E, you need to add the extra distance, the extra addition of the lever arm distance with respect to the bending moment. So it's WL square by 2 plus the remaining distance which is over here. So it has to be taken care that even the extra distances are considered. If it is bending moment at A, again WL square by 2 plus the extra distances that you are considering over there. Let's solve another example with respect to the shear force and bending moment diagrams for a cantilever beam. We have a cantilever beam, we have a uniformly distributed load for the entire beam span. Let's call this A, let's call this B, and let's combine it with a point load at point C of 2 kilonewtons. Let's say the UDL is 1.5 kilonewton per meter. And let's draw the shear force and bending moment diagram for this particular example. So before that, the regular drill, calculate the shear forces. Shear force at point B, at this particular point, we have a shear force at point B. We don't have any specific loads that are acting at this particular point B. So in order for the forces to right, let's calculate the shear forces. Shear force at point B. Since there is no support at point B, there is no reactive forces in response to the shear force that is happening with regard to the UDL. So on the free end, whatever UDL that is happening on the cantilever beam, the shear forces on the free end would be 0. So that is 0 kilonewtons. Moving on, shear force at C, right of C, just towards the right of C. Just towards the right of C, we have (1.5), that is the UDL, times 0. So I didn't mention the diagram, I mean the measurements. Alright, here's another example of a cantilever beam with a uniformly distributed load in combination with a point load of 2 kilonewtons. The total span of the beam is 2 meters. Let's just calculate the shear forces, bending moments, and let's just draw the shear force and bending moment diagram. So as you can already see, I have calculated the shear force at point B, that is 0 kilonewtons, because point B there is no lever arm, and whatever force that is happening, the shear force at point B will be 0. Shear force at C, towards the right of C, it is 1.5 times 0.5, because the length is 0.5 meter. So this will give us 0.75 kilonewtons. Since it's acting downwards, right hand side of the section is positive. Shear force at left of C, that would be again a UDL of 1.5. We have the UDL acting all the way across, so this would be a constant thing everywhere. So 1.5 times left of C, that is again 0.5, plus we have a point load of 2 kilonewtons acting downwards, so that is 2. Since it's a point load, it's constant, so there is no multiplication of value. Since it's a UDL, we'll have to multiply it with its applying span. For instance, shear force at right of C, we have multiplied 1.5 kilonewtons of UDL to its applied span 0.5, which gives us 0.7. Basically the shear force for UDL is WL, W times the span on which it is acting, and for point load it's just W, that is 2 kilonewtons over here, which is represented. Now this would give us 1.5 times 0.5, that is 1.75, 1.75 plus 2, that is 2.75 kilonewtons. Shear force at left of C, we have A, shear force at A. So the shear force at A, 1.5 times the total length, so that is 1.5 times 2 plus the force acting downwards, so it is positive, we have 2 kilonewtons, so this will give us 1.5 times 2 plus 2, 3 plus 2, that is 5 kilonewtons. So this is a shear force. Let's calculate the bending moment. Bending moment at point B. Point B, there is no lever arm, so bending moment at point B should be 0 kilonewton meter. Bending moment at point C. Point C, we have a bending moment of 1.5 kilonewton meter acting downwards. It's causing hogging, so it is negative. The bending moment formula for a uniformly distributed load is WL square by 2. So W is 1.5, L is 0.5 squared, that is 0.5 squared by 2. So that would be 1.5 times 0.5 squared by 2. And since everything is acting downwards, it's negative. So this would come to 0.187 kilonewton meter. Next, bending moment at point A, that is the last point. We have 1.5 times the total lever arm length, that is 2 meters, 2 square by 2 plus 2. We have minus 2 kilonewtons acting downward towards the lever arm of 1.5 times. So this would sum up to this is, I think this comes to minus 3 and plus into minus 3, that is minus 6 kilonewton meter. So this is the bending moment at point A, 6 kilonewton meter. Now let's just quickly draw the diagram. This is the fixed support, this is the beam, we have a UDL, have a point load, this is 1.5 kilonewton per meter, B, C, A. Just extend the lines. Shear force x-axis, bending moment x-axis. All the shear forces over here, they are all positive, so everything will be coming above x-axis. All the bending moments here are negative here, this is also negative, so everything will be coming below the x-axis. So for the shear force, point B, it is 0, so there is no change. Right of C, that is 0.7, let's just put that somewhere over here, 0.75. Left of C, it is 2.75, it's slightly more, so it's 2.75. And at A, it is 5, so let's just put this as 5 kilonewtons. So we have a UDL from between point B and point C. So for a UDL, the shear force would be linear, the graph would be linear. Again, we have a point load of 2 kilonewtons, so there is no linearity over here, it's just constant. So there is a quick bump of 0.75 to 2.75, so it is vertically upwards. Then we have another UDL acting from point A to C, so it's again linear. So I'm just connecting the linearity. So all of this is acting above the x-axis, so it's positive. Now coming back to the bending moment diagram, we have 0 kilonewtons at point B, so there's no change over there. Bending moment at C is minus 0.187, we'll just represent it over here, and bending moment at A is minus 6 kilonewton meter. So there is a UDL. The bending moment for a UDL beam is parabolic. So just put a parabolic figure over here, and there is an UDL between A and C, which is also parabolic. This parabola can change by a little bit because we have a point load over here. So the parabola can be a combination of linear linearly varying load and parabolically varying load. So since it's a hand-drawn diagram, it's not quite accurate, but if you ought to draw it in a much more robust softwares or applications, it would give you a much more clearer emphasis of how the parabola is changing with regard to the combination of different loads. So let's just quickly hash this. Since everything is happening below the x-axis, it is negative. Bending moment diagram, shear force diagram. Alright, welcome back. Let's quickly solve another problem, but this is with respect to the shear force and bending moment diagrams for a simply supported beam. So let's just have a simply supported beam that is supported on the two ends with 2 point loads somewhere in between. Let's give it 3 kilonewtons, 6 kilonewtons here. The spans between is evenly distributed. Let's put 2. Let's just give the A, B and C and D. So let's try to calculate the shear force and bending moment try to draw the shear force and bending moment diagram for this. First up, unlike your cantilever beam, we cannot directly calculate the shear force and bending moment here because we have the reaction loads acting from bottom. The reaction loads are nothing but these are the reactive forces that are happening in response to the oncoming loads, that is 3 and 6 kilonewtons acting from above. So basically the reaction, let's call the reaction loads as RA and RB. So RA and RB are the reaction forces for the loads that are acting from the above 3 kilonewtons and 6 kilonewtons. In other way, we can simply write it as RA plus RB is equal to 3 plus 6 kilonewtons. So everything should be in equilibrium. I'm not going to draw a separate diagram for bending moment and shear force. Let this be the diagram for bending moment. I'll be solving the rest of the problem onto the right hand side. So the first step in this particular example is I want to calculate what are my reactions over here. So calculate the reactions. So in order to know my reactions RA and RB, I am going to consider one particular point. Let's just consider point A, and I'm going to say that my moment, I'm going to assume that my moment at point A is equal to 0. I mean, for a simply supported beam, the moments at the ends are 0 anyway. So let's just say that moment at A is 0. So with that in consideration, let's calculate the moment at A with respect to the remaining forces that are acting from here. So RB into lever arm, RB into the lever arm, that is 2, 2, 2, that is 6, 2 plus 2 plus 2, that is 6, minus, why minus? Because there is a force acting from the above, so it is creating a hogging moment. RB is positive because it is creating a sagging moment, so that is positive. So minus 6 into 2 plus 2, that is 4. Again minus 3 into 2, so this would give us 6 RB minus 24 minus 6 equals to 0. The total moment at A is equal to 0. So RB will be equal to 24 minus 6, that is 30, 30 on the other side plus 30, RB is equal to 30 by 6, 30 by 6 is 5 kilonewtons is my RB. I know my RA plus RB should be equal to 3 plus 6, that is 9 kilonewtons. Since my RB is 5 kilonewtons, my RA should be equal to 9 minus 5, that is 4 kilonewtons. So now that I have my RA, which equals to 4 kilonewtons, and RB equals to 5 kilonewtons, I'm going to calculate my shear forces and bending moment with respect to these forces. So the next step is the generic way of how we usually calculate the shear forces, like your cantilever beam shear forces. Let's start with shear force at point P. Shear force at P, we have RP, which is acting from bottom to top. Now, if you can recall, on a section, if the force is acting from bottom to top on the right hand side and force is acting from top to bottom on the left hand side, it is negative. The shear force is negative. So RB over here is negative, and RP is nothing but 5. So I'll just directly put 5 over here instead of RB, minus 5 kilonewtons. Shear force at point T, towards the right of D, just towards the right of D. So just towards the right of D, it is the same force, since the shear force point load, for a point load, the shear force is constant, so that was minus 5 for point D. Left of D, shear force at D left, we have 6 kilonewtons acting downwards, opposing the force 5 kilonewtons acting upward. So this would be minus 5 kilonewton plus acting downward, right, 6 kilonewton, this would be 1 kilonewton upward and downward. Now shear force at right of C, since it's 1 kilonewton, it will be the same, since the shear force is constant for a point load, so it will be 1 kilonewton towards the right of C. Shear force at C left, we have 3 kilonewtons included acting downwards, so that is 1 kilonewton acting downwards, plus 3 kilonewtons acting downwards. Shear force towards the right hand side of the section acting downwards, it is positive. So, and we have 6 kilonewtons acting downwards, so this would give us 5, 6 and 3 towards the left of C. It is minus 5 upward and plus 9 acting downward. This is 4 kilonewtons. Shear force at point A should be the same, that will be reflecting all the way to the end, so that is 4 kilonewtons. Now lastly, let's just calculate the bending moments. Bending moment at point B. At point B, there is no lever arm. Whatever load that is happening on top should be equal to 0. So 5 times 0 is 0. Bending moment at D. So that is minus 5. That is 5 times the lever arm 2. We are not having minus over here because it is creating a sagging action, so it is positive. So plus 5 into the lever arm length, that is 2. So 5 into 2, that is 10 kilonewton meter. Next, bending moment at C. We have 5 times the total lever arm, so that is 5 times 4. 5 times 4, that is 20. We have 6. Now 6 is creating a hogging action, so it will be negative. 6 times 2, that is 12. So 5 times 4, 20. 6 times 2, 12. 20 minus 12, that should be 8 kilonewton meter. Yeah. Lastly, bending moment at A. This should be equal to 0. I mean, basically, for you really need not calculate the bending moments at the end supports, especially for a simply supported beam, because we know that for a simply supported beam, the moments at the support will be equal to 0 anyway. So you can spare the time to something else, drawing a better diagram rather than calculating the bending moments it supports for a simply supported beam especially. So now that we have our shear forces and bending moment, let's just draw the SFD and BMD. X-axis for SFD, X-axis for BMD. Shear force at B, we have -5. So since this is minus, it goes below the x-axis. This is your 0, -5. Let's just put that somewhere over here. -5 kilonewtons. Sorry, and then shear force at right of D, that should be over here. Again, -5 kilonewtons. Next, shear force to the left of D is 1 kilonewton. It has gone positive, so 0. Let's just put 1 as somewhere over here, 1 kilonewton. Shear force to the right of C, it's the same thing. Everything is point load, so it's all constant. So 1 kilonewton. Shear force to the left of C, it is 4 kilonewton. There is an increment. Let's just put 4 kilonewton somewhere over here. And shear force at A, again, it's 4 kilonewton. Since everything is point load, everything is a constant line, so there is no requirement for a linear lines here. This is your shear force diagram. The part which is below the x-axis is negative. The part which is above the x-axis is positive. Similarly, for bending moment diagram, let's just quickly put that here. The bending moment at point B and point A is 0, so you need not consider point B and point A in the diagrammatic representation. So bending moment at C, it's 8 kilonewtons positive somewhere. Let's just put over here 8 kilonewton meter, and 10 kilonewton meter positive. Let's put that 10 kilonewton meter. Bending moment at D. Just a small blunder. This is not 10. I just flipped it. So this should be 8 kilonewton meter, and this should be 10 kilonewton meter. So in that case, this is how your graph is done. Since everything is happening above the x-axis, it's all positive. You can disregard this black line. This is so. This is how you draw a shear force and a bending moment diagram for a simply supported beam that is subjected to point loading. Hello again. Let's come back to solving shear forces and bending moments and representing them in an SFD and a BMD diagram. So let's take another example. We'll be considering a simply supported beam this time, but with a uniformly distributed load. Let's solve a very simple example. We have two supports on either end. We have a beam that is resting on the support, and we have a UDL acting just somewhere up to point C. Let's call this A. Let's call this B. Let's call this C. And this is split by 6 meters, and let's just say this is split by 3 meters. So let us calculate the shear force and bending moment for this particular beam member and represent that in a diagrammatic fashion. So before that, we need to calculate the reactions first, because for a simply supported beam, we need to identify the reactions RA and RP first. So in order to calculate reactions, let's just assume the moment at point A is 0, and RP times the total lever arm, RP into 9, this is 1, and we have 10, sorry I didn't write this, it's 10 kilonewton per meter. RP into 9, that is total lever arm, plus 10 kilonewton per meter is the UDL acting downward, and we know that the bending moment, we know that the moment for a uniformly distributed load for a beam is WL square by 2, so that is 10 times 6 square by 2, so 10 into 6 squared by 2. Now it is acting downwards, so you might be wondering that since this is a simply supported beam and the load is acting from top to bottom, it is creating a sagging action, so it is positive. But here we are trying to calculate the moment at one particular point, and the load acting over here is causing a hogging action. Now with respect to the entire beam, yes, it is causing a sagging action, but with respect to only one support, it is causing a hogging action. So we go about with a negative 10 kilonewton per meter run. Complete sum of that should be equal to 0. So RB, 9 RB plus into minus 6 squared, 36 by 2, that is 18 times 110, that is 180 minus 180 equals to 0. I think RB should be equal to 180 by 9, that is 20. Yes, RB should be equal to 20 kilonewtons. And similarly RA plus RP should be equal to whatever load that is happening from the top, that is 10 into 6, we are multiplying the UDL times its total run, so that is 10 into 6, that is 60. So RA should be equal to 60 minus 20, that is 60 minus 20, that would be 40 kilonewtons acting at the bottom. RA is equal to 40 and RP is equal to 20. Now let's calculate the shear forces. To calculate the shear force, let's start with shear force at point B. Shear force at point B. Now we know the shear force at point B is a point load, that is RB, which is acting from down to top 20 kilonewtons, down to top on the right hand side of the section, so it is minus 20 kilonewtons. It is a negative. Shear force at C right, towards the right, it should be the same because nothing has changed in between, so it is minus 20 kilonewtons again. Next, shear force at C left of C. Now left of C or at A, both are the same. There's not much any difference anyway. So if you have to consider RB is minus 20 kilonewtons acting from downward, plus into we have 10 kilonewtons acting from top towards and on a span of 6 meters, so that is 10 times 6. So this would be minus 20 plus 60, that would be 40. And lastly, shear force at point A, it's the same thing, right, left of C or point A, it's the same thing, so it is 40 kilonewtons. So now that we have the shear force at different points, let's calculate the bending moments. Bending moment at point B, again simply supported, it's 0, there's no point in calculating. Bending moment at point C, that is at this particular point, so at point C, minus 20 times the lever arm, minus 20 into the lever arm, 3 meters, so that is 60 kilonewton meter. Since it's creating a sagging action, it will be positive, it will remain positive. And bending moment at A, we know that it is at the support, so it would be equal to 0 anyway. Next, now that we have the bending moments and shear forces, there is one important aspect that we need to discuss here. In this particular beam, there is a point where the beam will experience a maximum bending moment. I mean, we know that the bending moment at A and B is equal to 0, but between somewhere A and C, there is a point that it will experience the maximum amount of bending moment. So, if we can identify that particular point, we can represent the same bending moment. We can represent the same with respect to the bending moment diagram. We can show where exactly is the maximum moment happening in our shear force and bending moment diagrams. So let's just try to calculate the maximum bending moment over here. In order to do that, first let us consider a point, an arbitrary point at a distance of x from either end. Let's just consider from the end A. Consider a point at distance x. So from A, I'm going to consider a point somewhere in between at some distance x. From A. Now I'll be trying to calculate the shear force at this. I'll just try to put that over here, so it will be much more easier to. So this is my distance x, and let's just call this section xx. So distance x from the section to the section xx. So in order to calculate the shear force at x, at this particular point, at a distance of x, at section xx, I have my RA over here, and RA is acting upward. So left hand side of the section acting upward, it is positive. So that means that my RA is positive, minus I am having 10 kilonewtons acting downward. So the shear force of 10 kilonewtons acting for a particular distance of x, which is acting downward. So that is 10 times the span on which it is acting, that is x. So 10x, which is acting downward, that is why minus should be equal to my RA is equal to 40. So this can be written as 40 minus 10x. Right. Now that my shear force is identified at a distance x, the shear force is identified as 40 minus 10x. Now, in order to calculate the maximum bending moment, I know that the shear force would be 0. I mean, if you can just go through the literature and textbooks, we know that for any simply supported beam, in order to identify where exactly the maximum bending moment is happening, the easiest way to identify the maximum bending moment is the point where the shear force is absolute 0. So let's just equate that shear force at x, that is, let's just consider this arbitrary point, shear force at x is equal to 0. Now if we equate these two, that is 40 minus 10x equals to 0, your x will be equal to, putting on the other side, x should be equal to 4 meters. So x is equal to 4 meters. That means that at a distance of 4 meters from point A, you will be having a shear force that is absolute 0. There is no shear force at that particular point. Now it is at that particular point the moment will be at its maximum. Let's just try to represent that in diagram so that it will be much more easier to understand. So I'm just extending these lines all the way. this is my shear force diagram. I'll just put a little more. And this is my bending moment diagram. Shear force at point B, it is minus 20. We have all the way up to minus 40. So this is minus 20. Shear force at C. Shear force at C towards the right of C, again it's minus 20. Left of C, it is plus 40. So this is plus 20. I'll just put plus 40 somewhere over here. And shear force at A, it's plus 40. Since this is a point load acting upward, this would be on constant norm, and since this is a UDL acting from point A, between point A and point C, it should be linear. So we wouldn't be considering the point towards the left of C over here. We'll be considering the lowest and the highest point since it's a UDL. So I'm going to join these two over here. So as you can see, at this particular point, somewhere at a distance of x, at this particular point, the shear force is equal to 0. You can see that it is not on positive note, not on negative note, it is on absolute 0. So the shear force at this point is 0 kilonewtons. That means it is at this point the maximum bending moment will also occur. Now the distance between this particular point and point A is the distance x which we have considered, and the distance x is nothing but 4 meters. So this particular distance is 4 meters, that is x is equal to 4 meters over here. Now let's calculate the bending moment, the maximum bending moment as well. I'll just put it over here. Bending moment at x, that is 4. So that should be equal to RA times x minus, we have a UDL acting downward. So it is, for a UDL, bending moment is WL squared by 2. So W is 10, span is x, 10 into x square by 2, downward hogging. So this would be RA is equal to 40 times x is equal to 4 minus 10 into 4 squared by 2. This should give me 160 minus 80. This is 80 kilonewton meter. So the bending moment at x, where x is equal to 4, where my shear force is 0, the maximum bending moment is equal to 80 kilonewtons. That is, at this particular point, if I extrapolate this particular point, I'll be experiencing a maximum bending moment of 80 kilonewton meter. Let's just draw the remaining bending moments first to identify the remaining bending moment at B, that is 0, so it will be no change. Bending moment at A, that is 0, so there is no change. Bending moment at C is 60 kilonewtons positive, so 60 kilonewtons is somewhere over here. Let's just put it over here, 60 kilonewton meter. Since this is a point load, it will be linear. This is a UDL, it would be parabolic. So now if you see, the maximum bending moment is at here, that is 80 kilonewton meter, where the shear force is exactly 0 kilonewtons, and it is at a distance of 4 meters. Now you see how the entire working of this goes. At 0 shear force, the maximum bending moment occurs. In order to find the maximum bending moment, we try to calculate the distance between the support and the point where the 0 shear force is actually happening, and that is how we extrapolate the line to the moment diagram. So this is how you do this particular kind of example. Welcome back. So let us solve another example with regard to let us solve another example with regard to simply supported beam with the combination of UDL and a point load. So this is our example. We have two supports, simply supported beam. We have two loads that are acting from top, 2-point loads. One would be 50 kilonewton, the other would be 40 kilonewton. And we have a UDL that is spanning between these 2-point loads, which is of 10 kilonewton per meter, and the distance of the UDL span is 4 meters. The distance of this is 4 meters and the distance of this is 2 meters. So the total length would be 10 meters, and when it is split, it is distributed in this order. So let's just quickly define our points. Let's call this A, let's call this B, let's call this C and D. Now that we have our diagram in place, the first step is to calculate the reactions. So we have reaction RA and reaction RB. Now in order to calculate that, let us consider the moment at point A as 0. Now this will have as RB into total lever arm. If we are calculating the moment over here, RB times the total length. RB into the total length is 4, 4 and 2, that is 10, minus we have 40 kilonewton acting from top, 40 into the total lever arm, 40 times 4 plus 2, 8. Then we have a 50 kilonewton acting from top to bottom. Sorry, we have a 10 kilonewton per meter UDL that is acting from top to bottom. So UDL on a beam, that is WL square by 2. So that is minus 10 load into L square by 2. Now by doing WL square by 2, we would be getting the moment at this point. Now we need the moment at this point. So we have another 2 meters extra which has to be added into the lever arm part. So we will add the remaining 2 meters to it. Then we have a 50 kilonewton acting downwards at point C. So minus 50. Let me just put this in the bracket. Times 2, the lever arm, and everything should be equal to 0. So this will be 10 RP minus 320 minus 8 plus 2, 10, 10 tens 100, 4, 4, 16, 160. So I'll just put this as 10 into 8 plus 2. Or I can just simply solve it as in here 4 into 2, 8 plus 2. Minus 100 equals 0. Now on solving all of this, I'd be getting RB is equal to 50 kilonewtons. So this is my RB at 50 kilonewtons. Now to calculate RA plus RB is equal to the total load which is acting from top, that is 50 plus 40, 50 plus 40, and we have a 10 kilonewton acting on a span of 4 meters, so that will be 10 times 4. So that is a total of 40 plus 40, 80, and 50 is 130. So RA should be equal to 130 minus RB, that is 50. That would be 80 kilonewtons. So my RA is 80 kilonewtons and RB is 50 kilonewtons. So I have my reactions found here. So the next step is to calculate the shear forces. To calculate the shear forces, let's start with shear force at B. Shear force at B. So we have a minus 50 kilonewtons acting top in the top direction, because towards the right hand side of the section we have the force acting upward, which is a negative connotation, so that would give us minus 50 kilonewtons. Shear force at D right should be the same, 50 kilonewtons. There is no change in any force in between these 2 points. Shear force at D left. Now that we have included a 40 kilonewton towards the left of D, we have to consider the 40. So that is minus 50 kilonewtons plus 40 kilonewtons. That should be equal to 10 kilonewtons. Shear force to the right of C, C right. So we have minus 50 kilonewtons from RB plus 40 kilonewtons at point D plus 10 times 4 UDL, that is 10 spanning over the UDL of 4, plus another 50 kilonewtons acting from top. So the sign connotations, I hope you are able to correlate with the main principle. On a section towards the right hand side, the load is acting downwards, so it's positive. So it's positive here, it's positive, it has been positive here, so it is positive here. But over here on the right hand side, it is going upward. That is the reason why it is negative over here. So this would give us minus 10 plus 40 plus 50. That would be 30 kilonewtons. Next, shear force at C left. On the left of C, now that we have included the 50 kilonewton part, sorry, this should be left of C. We'll just put this as right of C. Shear force on the right of the C. So we don't have this 50 mold over here. So that would be minus 50 plus 40 plus 10 times 4. This should be equal to 30 kilonewtons, and this should be equal to 30 plus 50, 80 kilonewtons. So we have 30 kilonewtons here, we have 80 kilonewtons here towards the right and left of C respectively. Next, shear force at point A should be equal to minus 50 plus 40 plus UDL times length 10 times 4 plus 50. That would total to, it's the same thing, so 80 kilonewtons. So this is the shear force at RA. Next, moving on, let's try to calculate the bending moment. So the bending moment for a simply supported beam it supports is always 0. So bending moment at B is 0, bending moment at A is also 0. So the only bending moment that we need to calculate here is bending moment at point D and bending moment at point C. So in order to do that, BM at C, or okay, bending moment at C. So that is RB into 8. So that is minus, sorry, that is 50 into 8 minus, we have 40 kilonewton acting from top and we have a UDL that is acting. So 40 times 4, 40 times 4, that is the point load bending moment, and the UDL is WL square by 2. So 10 into 4 square by 2 minus 10 into 4 squared by 2. So you might have noticed that we have just did 4 square by 2 and we didn't add any lever arm because we are trying to calculate the bending moment at C. So the only lever arm we need to consider is this WL square by 2. And just for the fact that the reason why the WL square plays is that if we can split the WL square by 2 as WL into L by 2 for a UDL. In order to convert the UDL into point load, we do WL. When we do WL, the UDL will be converted into point load, and the load acts exactly at the middle of the span, that is length by 2. So the mid span will be length by 2. So in order to calculate the moment, we are basically converting a UDL into a point load and splitting the entire span by L by 2. So if you want to calculate the moment at A, the point load which is converted as WL now will be multiplied to the lever arm, which is L by 2. So ultimately you will be left with WL squared by 2. So that is the main principle behind the WL square by 2, which has been used in the problem here. Coming back, so bending moment at C, this would give us 400 minus 160 minus this can go twice into that, so 4 2 is 8, 80. So 400 minus 160 minus 80, that would be 400 minus 240, which is 160 kilonewtons meter, kilonewton meter. So 160 kilonewton meter is the bending moment at C, and similarly bending moment at D should be equal to RB into 4. That's quite straightforward. So 500 into 4, sorry, 50 into 4, that would be equal to 200 kilonewton meter. Now, it's in the moments here are positive because it is creating a sagging action, sagging, so it's positive. Similarly over here, it's hogging, that is the reason why it's negative and negative here. And 50 is again pushing from bottom, so it is positive over here. So we have the two bending moments, we have the shear forces, now that we have our shear forces, we need to calculate the point where the shear force would be 0. The reason for calculating the point where the shear force would be 0 is that we can get the maximum bending moment at a point where the shear force is absolute 0. So let's just assume that I'm just going to represent the same diagram over here with two loads and a UDL here. This is A, well this is B. Let's just take a section XX, and let's just consider the distance of this section to distance of X. So let us try to calculate the shear force at this particular point at a distance X from point A. Now the reason for calculating that is that when we calculate shear force at point X, we will be equating that to an absolute 0, so that once we equate that to 0, we'll be getting the distance of X. Now when we get the distance of the X, we'll know that the shear force at that particular distance will be will be 0 at that point, and at that point we can calculate the bending moment which is corresponding to the absolute 0 value. So let's just do that in this problem. Shear force at a distance of X should be equal to, we have RA is 80 minus, we have 50 kilonewtons that is acting from top, this is 50 kilonewtons, 50. So we're trying to calculate the shear force over here. So on the left hand side it is going upwards, so it's positive. Again on the left hand side it's coming downside, it's negative, minus 50. Again we have a UDL 10 into, yes. So here when we are trying to calculate the UDL part over here, we know the distance over here is 2 meters, this is 2 meter distance. Now whatever UDL that has been acting in which is contributing, the shear force that is contributed by the UDL is happening in this particular region, the region where the region between the 50 newtons and the section XX. So the distance between 50 newtons and section XX would be x minus 2. So the span on which the UDL is acting that contributes to the shear force is 10 times x minus 2, x minus 2. So this would give us 30 minus 10x minus 20, or this should be equal to, and all of this can be equated to 0 because we want to calculate at what distance the shear force would be absolute 0. So that would give us 10, this would be 20, sorry, so small, 80 minus 50 minus 10 times x minus 2 should be equal to 0, and x should be equal to minus 10x minus plus 20, this goes there, minus 20, 80, so this should be equal to, x is equal to 5 meters. So this is the distance of x where the shear force would be absolute 0. So at x is equal to 5 meters, your shear force will be equal to 0, and at that point the maximum bending moment will be occurring. So let's just calculate the maximum bending moment over here. Bending moment, maximum bending moment or bending moment at a distance of x. So this should be equal to RA. So let's just draw the same diagram over here. This is the distance x, bending moment at here. RA times the lever arm, that is 2 plus the remaining portion over here. RA into x, I'm sorry, the distance which we have considered till this point is x. Yeah. So RA into x minus 50 into x minus 2 minus, we have a UDL, 10 into, again it's acting in just that particular point between 50 newtons and the section XX. So that will be 10 into x minus 2 whole squared by 2. So this would be 80 into 5 minus 50 into x is 5 meters. So 5 minus 2 minus 10 into 5 minus 2 whole squared by 2. So this would give us a value of 5 8s are 400 minus, this is 3 times 50 is 150 minus, this is 3 squared 9, 10 by 2 5, so it would be 5 into 9 would be 45. So this should be 205 kilonewton meter. So 205 kilonewton meter is the bending moment at x, and that is the maximum bending moment that can occur. So if you are to draw the SFD and BMD diagram, we have the axis of shear force and axis of bending moment. So the axis of shear force, let's quickly plot that. We have a minus 50, let's just consider minus 50 over here. I'll just extrapolate the remaining lines. This line represents the distance x from point A. So we have minus 50, then we have to the right of D another minus 50, Then we have left of D minus 10, so that will be somewhere over here. Then we have 80, that is to the left of C, that is somewhere over here. I'll just put 80 over here. Then to the right of C we have 30, again we'll drop down somewhere over here, and at A we have 80. So let's just join. Since it's point load, it's constant over here, it's constant till here. Again, UDL, the load is linear, so it's not constant there. Then we have a point load here, so it's constant. We have a point load there, so it's constant. So this is our shear force diagram. Quick hatching. Now if you see at this particular point, the shear force is absolute 0, and this point is at a distance x. So that is a point where the distance is at x. So the line which we initially drew, this particular line should be slightly towards the right hand side. So this is the point where the x is. So x is equal to 5 meters, and at 5 meters the shear force is absolute 0. Now coming back to the bending moment at point B and point A are zeros, so we can just put that at 0. Bending moment at C is 160, bending moment at C it's 160. Let's put that somewhere over here, it's positive, so it's up. Next, bending moment at D is 200, bending moment at D slightly above 200 here. And the maximum bending moment, that is at x, is 205. So at x, this is this point, it is 205, slightly above 200, 205, 200 and 160. So let's just join all the lines. Point load bending moment, it's linear. Again we have a point load bending moment is linear. But over here it's a uniformly distributed load, so the bending moment is parabolic. So at this particular point, this is the point where the maximum bending moment is occurring. So at 0 shear force, the maximum bending moment is 205 kilonewton meter. So that is how you need to calculate the bending moment, the maximum bending moment, in order to plot it on a shear force and a bending moment diagram. So let's solve another example, but this time let's slightly do a different kind. Let's incorporate an overhanging beam in this particular problem. So let this be a beam. Let's have two supports with the overhanging portion. We have a point load of 1000 newtons at one end, and we have another point load of 800 newtons. We have another point load in the middle of 2000 newtons. This is 3 meters, this is 5 meters, this is 3 meters, and this is 2 meters. Let this be RA and this be RP. Let's identify our points as C, A, D, B and E. So in order to solve this, it's all the usual drill. We need to calculate the reactions first, followed by shear forces, then followed by bending moments, followed by maximum or minimum bending moment, whichever that comes. So first point, calculating shear forcing, calculating the reactions. Let the moment A is equal to 0. So that is RB we're calculating the moment at this point. So RB into total length, RB into 8, 3 plus 5, plus we have 1000 newtons acting downward, so that would be minus 1000 acting downward times the total length, 3 plus 5 plus 2, that is 10, plus into we have 2000 acting downward, so that is minus 2000 times 5, and then we have 800 times the distance 3, and everything together should be equal to 0. Here's something that's a little different that we have to do. The thing is that when we are considering the forces on the overhang portion, if you consider the force of 1000 newtons on the overhang portion, let's just say this is the overhang part and this is the load of 1000 newtons acting. So when a force of 1000 newtons is acting at this particular point, it is turning the entire beam in a clockwise direction. It is creating a hogging movement, and also it is creating a clockwise directional movement. And similarly on this end, the force of 800 newtons is creating an anti-clockwise movement, and also it is hogging. So since there are two kinds of directional movements, you will have to consider either one of the movement as an opposite sign of the other. So over here we have considered minus 1000 newtons into the total lever arm. So here we will have to consider 800 newtons as positive into the lever arm 3. So because the moments, you cannot have two different moments in acting in the same sign convention for this particular, in the same beam span. So in that case, we converted the minus into plus over here. So we'll be left with 8 RP minus 10,000, again plus and a minus, minus 5 to 10,000 plus 2400 equals to 0. So RB should be equal to 20,000 minus 2,400, that would be about 17,600 divided by 8. This should be 2,200 newtons. Similarly, RA should be equal to 2,200 minus the total load that is acting from the above, that is 800 plus 2000 plus 1000. Or this should be plus, this should be minus. All this together should be coming up to 1600 newtons. So this is your RA and this is your RB. Let's just put that RA is equal to 1600, RB is equal to 2200. So now that we have our reactions, let's calculate the shear forces. Shear force at point E, 1000 newtons, straightforward, positive. Shear force at B, towards the right of B, just towards the right of B. So it would be the same, there is no change in between, 1000 newtons. Shear force to the left of B, we have an inclusion of 2200 newtons over there. So that would be 1000 minus 2200. This would give us 1200 minus 1200 newtons. Next, shear force at right of D, it would be the same, reflecting all the way to the point D. Shear force to the left of D, we have an inclusion of 2000 newtons again from top, so that would be minus 1200 plus 2000, so this would be 800 newtons. Then shear force at right of A, again it is the same thing, no change. Shear force at left of A, again we have 1600 incorporated over there, so it's 800 newtons plus 1600 newtons. So that would be, sorry, it's 800 newtons minus 1600 newtons because it is acting from bottom to top, and left hand side of the section, since it's going upward, it will be negative. So that would give us minus 800 newtons. And shear force at point C, it will reflect the same thing all the way till the end. So 800 newtons. 1000, 1200, 1200, 800, 800. So we have our shear forces. Let's calculate the next step, bending moment. Now the bending moment at the free ends C and E will be 0 because we are not having any lever arms over there. So let's just not calculate bending moment at E and C, which is always 0. So bending moment at B will directly go to B, that is minus 1000 times the lever arm 2000 hogging action, so minus. So this will be minus 2000 Newton meter. Bending moment at D should be equal to minus 1000 times 5, because 2 plus 3 is 5, plus 2200 times 3. Since it's creating a positive moment, it is positive. So there should be 5000 plus 6600. 6600 minus 5000, that will be 1600 Newton meter. And bending moment at A, I'm just going to put it over here, should be equal to 1000 into the total length, that is 10, minus plus 2200 times 8, minus we have a 2000 times 8, sorry, 2000 times 5, and this would give us 10,000, and this is another 10,000, so that would come to 2400 Newton meter minus. So we have our bending moments 2400, 2000 and 1600 Newton meters. Now that we have bending moments, let us calculate an important aspect of this particular example. It is the point of contraflexure. So in order to define point of contraflexure, we need to understand that when there are forces that are acting in this order, and alternating forces, or if there is any stresses that are alternating, there is an instance in the beam where the moments will change from its negative connotation to positive connotation. Now when this change happens from negative to positive or positive to negative, it has to happen through the point 0, and it is at that point, that particular point 0, we call it as the point of contraflexure. To keep it on a much more refined definition, it can simply be defined as a point where the bending moment is 0 after changing the sign from positive to negative or negative to positive. So let's just visually identify that particular point, the point of contraflexure, and represent it in our shear force and bending moment diagram. So in order to do that, we need to calculate the point of contraflexure. So this would be your fourth step to calculate the point of contraflexure. Now to do that, let us draw a rough diagram of the same. And let's consider a section XX, just like your previous examples. Let's consider a section XX at a distance of small x. Now from this is A and this is B. From support A, let us identify where exactly the bending moment is happening with respect to support A and section XX. So bending moment at cross section xx, that is this, we are trying to find the bending moment at this point. Bending moment at cross section xx should be equal to, we have 800 newtons over here and we have 1600 newtons over here. So that is minus 800 times the lever arm. We need the length of this particular span. So the lever arm for this is, small correction, it is, we need to consider the distance from the support, not from the end point. So x should be this point here. This is your x. So with that in place, let's just put the distance over here as 3. We have 3 over here. So the lever arm here with respect to 800 newtons acting downwards is 3 plus x. So that will be 3 plus x. Right. Next, we have Ra, that is 1600 acting upward to the point of x, section xx. So upward 1600 times the lever arm, which is x. The distance is still x over there. And we can just solve this. 2400 minus 2400 minus 800x plus 1600x. Right. So that's pretty much it. We can solve this to get minus 2400 plus 800x. So this is the bending moment at section xx. Now we defined the point of counterflexure as the point where the bending moment would be absolute 0. So if we are to equate this equation to 0, we would be finding the value of x, which is nothing but the distance of the point of counterflexure from your support A. So on doing that, we'll be left with 24 goes to the other side, 800 goes below. So that would be x 2400 divided by 800. So that is about 3 meters. So x is equal to 3 meters. It means that from point A, let's put this over here, from point A at 3 meter distance, your point of counterflexure is occurring, and at that particular point your bending moment will be absolute 0. So let's just put that in diagram as well. There is a possibility of having another point of counterflexure in the same beam, since we are having the same alternating loading that is happening throughout the entire span. So let's just calculate that as well on another side over here. Bending moment at section xx, but with respect to Rp. So if we are to consider section xx with respect to Rp, we'll be having minus 1000, that is minus 1000 times the distance, sorry, with respect to Rb, not this 1000, so this 1000. So let's just quickly draw this on the shear force diagram. Your shear force and your bending moment. So shear force at E shear force at E is 1000 newtons, so it's positive 1000. Then we have at B right again 1000. Then B left we have minus 1200, so that goes down here, minus 1200. Then we have another minus 1200 at D right, so minus 1200. Then we have D left 800, so it's going back to positive again, somewhere below 1000, 800. Again we have A right 800. Again we have A left minus 800, again going to negative. And lastly we have 800 on this. So let's just since everything is point load, there's not much to worry about linear graphs or linear charts. So this is our shear force diagram. Let's calculate the bending moment. We have bending moment at B. Bending moment at B is minus 2000. So this goes below. So I'll put the bending moment in a different ink. So let's just consider this is minus 2000. Then we have bending moment at D at 1600. Bending moment at D at 1600, somewhere over here. Then we have the bending moment at A as minus 2400. Bending moment at A minus 2400. And the bending moment at point E and point C are 0 anyway, so I'll just put that. Now it is linear, the bending moment. So this is our bending moment diagram. Now if you identify at this particular point the bending moment is equal to 0. Now it is this point is what we determine as the point of counterflexure, and this point is exactly 3 meters from our support A. So the distance between the point A and the point of counterflexure is 3 meters. So I can just represent that over here. That is the distance of point of counterflexure from point A. So we can just put that over here, 3 meters, somewhere over here. So that is the point of counterflexure. As you can also see that there is another point of counterflexure over here. There are 2 points of counterflexure for point A and for point B as well. So the procedure is the same. You need to calculate the second point of counterflexure with respect to the point support B. So you just have to consider another section somewhere over here, and you'll have to calculate the distance x with respect to the point B. You have to calculate the moments just like you did in calculating the point of counterflexure for bending moment at cross section x6. You will have to calculate the bending moment of cross section x6 for point B with reference to point B. So you get the 2 points of counterflexure for A and B. So let's solve another example here. So we have an overhanging beam with 2 supports RA and RB with an overhanging portion of 2 meters outside RB. We have a point load of 2 kilonewtons and a UDL of 2 kilonewton per meter all across the beam. The entire span of the beam is 4 plus 2, 6 meters in total. So let's calculate the shear force, bending moment, maximum bending moment, and let's represent that in a SFD and a BMD diagram. So starting the first step, let's calculate the reactions. Moment at A is equal to 0 in that case. RB into 4 RB into 4, since it's causing a positive moment, sagging, that is why it's positive, minus, I have a 2 acting all across this point, so 2 times 2 plus 4, 6, with reference to the point load. Next, I have a UDL. So UDL, the moment for a uniformly distributed load on a beam is WL square by 2. So that is 2 into 6 square by 2, which is acting all across, and altogether should be equal to 0. So that would give us 4 RB minus 12 minus 36 equals to 0. RB equals to 48 by 4, that would be 12 kilonewtons. So my RB is equal to 12 kilonewtons, therefore my RA should be equal to, my RA plus RB combinedly, it is equal to 2 newtons acting from top times the entire UDL, 2 into 6, this is a positive plus, so this would give us 14. RA is equal to 14 minus 12, that is 2 kilonewtons. So my RA is 2 kilonewtons, my RB is 12 kilonewtons. Now let us calculate the shear forces. Shear force at C, didn't name this, so let's put this as A, let's put this as B, and obviously C. So the shear force at C should be equal to the point load that is acting, that is 2 kilonewtons. Next, shear force at B, we can put right of B. So just to the right of B, it's the same thing, 2 kilonewtons, but there is also a UDL that is acting across. So it is acting on a span of 2 meters, or 2 kilonewton per meter acting on a span of 2 meters. So that is 2 into 2, that would be 2 plus 4, that is 6 kilonewtons of shear force at B right. Shear force at B left, we have a 6 kilonewtons in addition to the 12 kilonewtons acting from bottom. So that will be 6 minus 12 kilonewtons, minus because on the right hand side of the section you have a shear force going upward, so that is why it is minus. So that will be minus 6 kilonewtons. Next, shear force at A, shear force at point A would be equal to 2 plus 2 times 6 minus 12. So we have a 12, 2 times the entire 6 and 2. 2 is the point load with respect to this, 2 times the entire 6 is the UDL with respect to the entire span, and 12 is RB with respect to the support. So on the whole we get 12 and 12 will be cancelled, 2 kilonewtons. So these are the shear force values, 2, 6, minus 6 and 2. Let's calculate the bending moment. Bending moment at C, since there is no lever arm over there, 2 into 0, that will be 0 kilonewton meter. Bending moment at B, that would be 2 acting downward, creating a hogging action, so minus 2 times 2 plus, we have a UDL that is acting, so that is, we have a UDL that is acting, so that is 2 into L squared, that is 2 square by 2. This is another one, again this is creating a hogging action, so it will be minus 2 on the whole. This would be minus 4 and minus 4, so minus 8 kilonewton meter. Next, bending moment at A, bending moment at A. Similarly, minus 2 times the total length 6 minus 2 into WL square. L is 6 by 2 plus we have a 12 that is acting from bottom into the 4. So this would give us minus 12 minus 36 plus 48. So this is minus 12 and 12 minus 48, and that is plus 48. So that would give us a 0 kilonewton at point A. So at point A we'll be having 0 shear force, while at point C we'll be having at point A we'll be having 0 shear force, and point C, my mistake, at point A we'll be having 0 bending moment, and at point C we'll be having 0 bending moment. Lastly, let us calculate the distance at which the shear force becomes 0, at the same time the distance at which the bending moment would be maximum. So shear force at a distance of x. So let's consider with respect to the support RA. It would be much ideal to draw the shear force and bending moment diagram first and then come to this, because then you would be knowing exactly which forces to consider to calculate the distance of x. We can take a section anywhere across this the entire beam, but it would be more appropriate if we can identify the near accurate point where the shear force would be 0. So I'll just draw the bending moment, shear force and bending moment diagram first, and then I'll come back to calculating the distance at which the shear force becomes absolute 0. So just put this as my SFD and BMD axis. So my shear force, let's calculate my shear force at C, that is 2 kilonewtons. So since this is 0, I'll have 2 kilonewtons over here. Then shear force to the right of B is 6 kilonewtons, somewhere over here, 6 kilonewtons. Shear force to the left of B is minus 6 kilonewtons, so again it goes to negative, somewhere over here, minus 6. Shear force at A, that is 2 kilonewtons, again it is positive, somewhere over here, 2 kilonewtons. Now I'm having a UDL and a point load in combination. So since there is a UDL, I'll be having my graph linearly varying, and the effect of point load will try to reduce the slope of the UDL by a certain degree, but not to an extent where it is visible. So let's just draw a slope of the shear force, which is linear because of the UDL happening. And at point B we have a force acting exactly vertically upwards, so there is no linearity over here, it's just a quick jump. And lastly, from 2 to 6 we are having a linearly varying graph at this particular point. So if we shade that, you can see that we have a point where the shear force is absolute 0, this point. Now it is easy to identify this point as we can represent it diagrammatically. So it will be much more cleaner, the diagram would be more accurate if we ought to do this first and come back to calculating the distance of the section XX. So now let's consider the distance of X from the support RA. Now calculating the shear forces at XX. Shear force at a distance of x, shear force of x is equal to, we have RA happening from bottom to top, that is 2 kilonewtons. Then we have a UDL of 2 kilonewtons acting from top to bottom. So 2 times x, it is acting on a span of x. Since it is acting vertically upwards on the left hand side of the section, it is positive, and similarly it is acting vertically downwards on the left hand side of the section, it is negative, the UDL is negative. So on the whole, the shear force at point x is equal to 2 minus 2x. Now we know at a distance of x the shear force is absolute 0. So we will equate this equation to 0 and we calculate x. X should be equal to 2x by 2, so x is equal to 1 meter. So the distance of x from point A is 1 meter. Now that we have the distance of shear force, we can also calculate the bending moment, the maximum bending moment. We'll try to draw the bending moment diagram first, just like we did for the shear force. Bending moment at C is 0, bending moment at A is 0, bending moment at B is minus 8 kilonewtons. So this is going negative, minus 8 kilonewtons. Let's put somewhere over here. And yeah, so we just have 3 bending moments over here. Now let's identify the bending moment at the shear force 0 point. So bending moment at distance x, which is nothing but the maximum bending moment, is equal to x is equal to 0 this is calculating point of contraflexure. So the maximum bending moment is equal to RA times x. So RA times x plus we have a UDL, that is 2 into it's spanning on x, so x squared by 2 will be the total bending moment over here. So this is a minus 2 since it's acting vertically downwards. So this can be written as RA is equal to 2x, I mean RA is 2 into x is 2x minus x square, since x is equal to 2, sorry, x is equal to 1, this will be equal to 2 minus 1, which is equal to 1 kilonewton meter. So the bending moment at that particular point is 1 kilonewton meter. So this is minus 8, this is 0, so let's put this as 1 kilonewton meter. Now let's join this. Since it's a UDL, the graph will be parabolic. Similarly over here, parabolic, and since this is the maximum bending moment point, this would be parabolic. This is the point where the bending moment is maximum. Just hatch this. Now looking at this diagram, we can also say that there is a point of contraflexure over here, point of contraflexure. Now we can also identify this particular point, the point of contraflexure, by considering the same steps we have followed in the previous example. So at this particular point, the bending moment will be absolute 0. So we try to calculate, we try to equate the moment to 0 with respect to the lever arm which we are considering from that particular support. So we'll just skip that part for this particular problem, but it would be nice to calculate all the data that can be extracted from the given beam example. So with this, we'll conclude this particular example. We'll come back for another example again. Welcome back. So we're back with another example of an I section. So what we intend to find in this particular example is that whether this I section is capable of carrying a point load with some given factors. This is the cross section of the I section, and this is the longitudinal length of the I section, which is 12 meters. The cross section, the width of the bottom flange is 100 mm. It is a symmetrical I section, so everything is mirrored on both the sides of this section, both on top and bottom and left and right. So 100 mm is the width of the bottom and the top flange. The total depth of the I section is 225 mm. The thickness of the bottom and top flange is 11.5 mm, and the thickness of the web, that is the middle part, is 7.5 mm. So this is basically a symmetrical I section, and the maximum allowable stress for this particular I section is 80 Newton per mm square. So that means that that is the maximum possible stress this I section can take with any form of loading that can occur on it. So the question basically is asking that if we introduce a concentrated load on this particular I section at a point at a certain distance away from its supports, would this I section be able to take? And if it can take, what can be the amplitude? At what magnitude of that particular point will be possible? So, for instance, let's just put this in a free body diagram. We have a span of 12 meters, simply supported on both the ends, and the question says that if we introduce a point load, a concentrated or a point load at a distance of 4 meters from one end of the support, let's call this support B and let's call this support A. From support B, if there is a point load acting at 4 meters from support B, what would be the magnitude of this load W? This is the question that is asked. We need to calculate the magnitude of the concentrated load for a given I section's geometry and its maximum allowable stress. So in order to do that, 12 meters, I have just split it into 8 and 4, where the point load is acting, which is 4 meters away from point B. So let's directly jump into the calculation of this. For this, we know that we have supports and we have support reactions. Now there is a possibility of support reactions for RA and RB. So we need to calculate those first in order to get the possible moments, So to calculate the support reactions, I'm going to assume that the moment at one end, let's put A, is 0. So with that, RB times the total lever arm, RB into 8 plus 4, that is 12, minus I have a load that is acting W, that is the unknown, vertically downwards, and it is causing a hogging action, so it is negative, minus 8. Now the total moment would be equated to 0. So 12 RB minus 8 W is equal to 0, and 12 RB minus 8 W is equal to 0, and RB is equal to 8 W by 12. This can be written as 4 by 6, or it can be simplified to 2 by 3 W. My RB is equal to 2 by 3 W, and I can calculate my RA, because my RA plus RB is equal to the total load that is acting from the above, that is W. W is the only load that is acting on above. So RB is equal to RA is equal to W minus RB, that is 2 by 3 W. This would give 1 by 3 W. No, I think it's not 1 by 3 W. should be 1 by 3 W. Now let's calculate the bending moment at C. Now that we have point A and point B, let's calculate the bending moment at point C. Which is equal to RP into the lever arm 4, which is equal to 8 by 3. Sorry, RB is 2 by 3 times 4. So it gives us 8 by 3 W. The units is Newton meter. So bending moment at point C is equal to 8 by 3 W Newton meter. We can convert that into Newton millimeter, which would be much more convenient for solving further. So 8 by 3 W into 10 power 3 Newton millimeter. Just converted meter into millimeter by multiplying 10 power 3 times. So now that we have our reactions and moments ready, let's calculate the next important factor, that is the moment of inertia, which can be represented with I. Now we know the moment of inertia for a rectangle is equal to BD cube by 12. Now for an I section it's slightly different. Thing is that if we ought to consider a rectangle, we will be considering the BD cube by 12 formula. If we ought to consider this entire portion. Now since this is the I section, a simple way to identify the moment of inertia for a symmetrical I section especially is we calculate the BD cube by 12 for the entire rectangular part and we minus these negative spaces from the entire BD cube by 12. So to do that, we can simply, this is the capital B and this is the small b. You can just write this as small b and this is a capital B, and this is the capital D and this is the small d. So in that case this would be B minus B times D minus D cube by 12. B minus small b gives the negative spaces, D minus small d gives the negative spaces. So this can be simply written as 100, that is total width, into 225 cube, that is the total depth, BD cube by 12, minus capital B, that is 100, minus small b, that is 7.5, times capital D, that is 225, minus the small d. We don't have small d, so what we are going to do is that we are going to add the two flange widths minus two flange widths, that's 2 into 11.5 whole cube by 12. So let's solve this. So on solving, I'm having 313,866,47.4 mm to the power of 4. So this is the moment of inertia I've got for a symmetrical I section in this example. Now coming back to our base formula, m by I is equal to sigma by y. We know m from here, we know I from here, we know sigma, that is given in the question, 80 Newton per mm square, and y, which is the distance of the neutral axis to the outermost fiber. I can just represent that with red here. If this is the neutral axis, the distance from the outermost compressive fiber, from the outermost beam fiber to the neutral axis, that is the distance. So basically this is y by 2, the total distance divided by 2. So, we will be having 225 divided by 2. So, putting that in the formula, we have 8 into 10 power 3 by 3, this one 8 into 10 power 3 by 3 to W, that is nothing but our W over here, divided by the moment of inertia 3138667.4 equal to the stress, that is 18 Newton per mm square. So, I am just directly putting 80 since it is in mm square, no unit conversion required, by 225 by 2. Yes. Now, solving for W would give me the total allowable load that can happen, the total point load that can be allowed for this particular cross section, which is having a maximum allowable stress of 80 Newton per mm square. So, that will be your answer, whatever W we get. We will just quickly calculate that. So, I am getting a W of 8,369.7 newtons. This is the load that can be allowed at this particular point, where my W is equal to 8,369.7 newtons. So, this is how you need to calculate for a symmetrical I section. So, we are back with another example. This is a asymmetrical I section which has different sizes with respect to its flange thickness and flange widths. It has the same web thickness. So, let us try to do a problem with an asymmetrical I section. So, the problem states that a cast iron beam of an I section is shown as shown in the figure. The beam is simply supported on a span of 5 meters. So, on a span of 5 meters, let us just say this is a span of 5 meters, it is simply supported on both the ends. If the tensile stress is not exceeding 20 Newton per mm square, so they have determined a tensile stress of 20 Newton per mm square. So, the stress is not to exceed 20 Newton per mm square, that is the cap which we have on the tensile stress, the permissible tensile stress on the entire I section. Find the safe uniformly distributed load which the beam can carry. So, the question says that we need to calculate the uniformly distributed load in W per meter for a span of 5 meters, where a beam of this cross section has a total allowable stress of 20 Newton per meter square. So, this is our basic question that we need to solve for. So, let us just identify the given data. We are given with all the dimensions and geometries of the I section, the asymmetrical I section. We are given with the allowable stress of 20 newtons per meter square, per mm squared, sorry. And now we need to calculate the maximum allowable uniformly distributed load that can happen across the entire beam. So, the principal formula behind this is the m by I is equal to sigma by y, where we will try to calculate the load W from the moment equations. So, out of all these we have sigma, which is already given, we can calculate y, but we need I. The I part over here is one that takes a lot of time in calculating, because we need to calculate the center of gravity of the entire section first, and then we need to calculate the individual moment of inertia of individual sections. So, let us just calculate the center of gravity of the entire asymmetrical I section first. So, in order to calculate I, we need the center of gravity Cg of I section. Let us call that y bar here. So, the Cg of an asymmetrical I section is given by, since we have 3 sections here, let us name this as O1, 2 and 3. Area of section 1 times y1, where y1 is basically the center of gravity of individual sections. For instance, the A1 Y1 means the area of the section 1, and Y1 is the center of mass or the center of gravity of this section only. So the center of gravity of this rectangular section is 40 by 2. So that will be over here. This is the center of gravity of section 1. Similarly, for the second section, it is A2 Y2. Y2 would be exactly at the center, and similarly for the third, it is A3 Y3 divided by all the areas combined. So on solving this, this will give us the center of gravity or the center of COG of the entire asymmetrical eye section. Let's just put everything into perspective. So A1, we have 160 times 40 into Y1. Y1 is half of 40, so that is 40 by 2. It's exactly in the middle for rectangle, plus A2. Sorry, I didn't put this value here. This is 200. Yeah. So A2 is 200 times 20 into 200 by 2, because the center of gravity is exactly at half over there. Now, when we do 200 by 2, this is giving the center of gravity of this particular section. Now, we have to do that with respect to the entire remaining portion of the section. So, it is 200 by 2 plus whatever that is remained below, that is plus 40. Okay. Similarly, A3 by 3, where A3 is 80 times 20, 80 into 20, into the center of gravity is 20 by 2, 20 by 2 plus 200 plus 40. Divided by all the areas combined, 160 into 40 times 200 into 20 plus 80 into 20. Now, on solving that, I have already solved this. So, solving the entire thing will be deduced to an answer 90.66 mm. So, at 90.66 mm from the bottommost fiber, that is from this point at 90.66 mm, let's just say that 90.66 mm is somewhere over here. At this point, we have our center of gravity for the entire asymmetrical eye section. So, the reason for calculating the center of gravity for asymmetrical eye section is that we would need this to calculate the moment of inertia of individual eye sections, and that has to be in reference to the center of gravity of the entire eye section. So, let's calculate the moment of inertia for this problem. The moment of inertia for the entire eye section should be equal to the inertia of individual sections. So, that is I1 plus I2 plus I3. So, for I1, the moment of inertia, it would be the moment of inertia of the section plus the moment of inertia of the entire asymmetrical eye section. So, the moment of inertia of the section, since this is a rectangular section, it would be BD cube by 12. So, BD cube by 12 plus the moment of inertia with respect to the entire section, which would be A1, let's call it H1 squared. So, basically A1 is nothing but the area of the first section, and H1 square is the distance of the center of gravity of this particular section and the neutral axis. For instance, let's just say the center of gravity of the section 1 is somewhere over here. Now, the distance between the COG of the entire eye section, that is in red, and the distance of the COG of the individual rectangular section. We need the distance between these 2 points, and that is nothing but 90.66 minus 40 by 2, that is 20 over here. So, that would be your H1 for this particular with respect to section 1. Similarly, it will be BD cube by 12 plus A2H2 and A3H3 whole squared for the respective I sections. So let's just put this into calculations. 160 times 40 cube by 12 plus A1, that is 160 into 40, into H1, that is the difference between the center of gravity of the entire I section 90.6 minus the center of gravity of the individual section, that is 40 by 2. So on solving this, like I said, already done before, so this would give me 32807481.1 mm power 4. So this is a moment of inertia for the section 1 part, that is I1. So I1 is equal to 32807481. Similarly, we need to calculate I2 and we need to calculate I3 for all the sections combined. We'll do I2 and I3. I have already done this, so we'll just try to solve I2 as well. I'll just directly put the value for I3 here. So for I2, let's calculate. It is B2 D2 cube by 12, or you can just put B1 D1 cube here, B2 D2 cube by 12 plus A2 H2 squared. Again, for section 2, let's calculate the width, which is 20, the depth, which is 200 by 12 plus A2, that is again 20 into 200 into, we'll just put it over here, into H2, which is nothing but the difference between the center of gravity of the entire section and the center of gravity of the individual section 2. So the center of gravity of the entire section is 90.66 minus the center of gravity of the individual section is 200 divided by 2. Now, just like how you did for your center of gravity of the entire I section, you have to add the remaining portion of the bottom part which is left with reference to the bottommost x-axis. That is 200 by 2 gives the center of gravity of the second section plus the remaining 40 mm which is there, for which is nothing but the depth of the remaining section. So 200 by 2 plus 40. This can give us an answer. Of 20 into 200 cube by 12 plus 4000 2. This is whole squared. 140 minus 90.66 whole squared. So the whole answer would come up to 2307107.7 mm power 4. This is your I2 and this is your I1. And lastly, for I3, the value is coming somewhere between 4067611.2 mm power 4. That is the I3. So we have I1, I2 and I3 with respect to individual sections. Now we need to combine all these three together in order to get the total I value. So I'll just put it over here. I is equal to summation of all the I1 plus I2 plus I3. That would give us 9655466.7.21 mm power 4. This is the the total moment of inertia for the entire section, asymmetrical I section. Now let's continue this problem. Now that we have our moment of inertia, we have our stress, we need to calculate the moment that can be happening over here. Let's come back to the base formula. M by I is equal to sigma by y, where you're given your sigma value, can calculate M by sending I to the other side. So M is equal to sigma by y into I, that will be 20 by y, which is 90.66. It is the distance of the neutral axis to the outermost fiber, that is 90.66, into I we have got as I as 9655466.7.2. So on solving this, 21300,389.8 Newton millimeter. So this is the moment that can be generated in this I section with of a span 5 meters. And now that we have our moment over here, we can calculate the W with a very simple approach. We know that for a simply supported beam with a uniformly distributed load, the maximum bending moment is given by WL square by 8. That is, if a simply supported beam with a UDL is present, the maximum moment is WL square by 8. Now, we have the moment of 213,00389.8 Newton per mm. We can just equate that to this and calculate the W over here. So for that, let's quickly equate the moment. Moment is equal to W into L is 5, because the span is 5. We have span 5 square by 8. This can be given as 3 5 5 is 25, that would be 3125 W Newton millimeter. So this is the moment with respect to the formula WL square by 8. Now we have the moment with respect to the moment of inertia which we got. When we equate these two moments, we can simply calculate the W. So W equals 213,00389.8 divided by 3125. This would give us 6816.1 Newton per meter. Right. So 681.6 Newton per meter is the total uniformly distributed load that can be allowed for that particular beam. I have converted this into Newton per meter. You might be getting a Newton per millimeter with a different value, slightly with a higher degree. That's all right. Convert it into a smaller number. It should work well.